Alright, in this video we're going to talk about exponential functions. It says exponential functions are functions having a variable in the exponent. We say that y equals f of x equals b to the x is an exponential function. We can use the y notation or the function notation. If b is some constant, that's a fixed value, like the number 3, where b is greater than 0, so no negative bases, and the base cannot be 1, or b cannot be 1, because 1 to any power is just 1. So on the left here, we have some examples of exponential functions. Notice the first one, y equals 2 to the x. 2 is a positive number, and it's not 1. Same thing with 1/3 to the minus x. G, be careful there, the base is actually just the 6, and so you do have a positive base, and it's not 1, so these are all exponential functions. Now on the other side, notice y equals x squared. Well, that's a variable, it's not a constant. And here we have the problem that the base is negative. And once again, the base here is not a constant. So these are all not exponential functions. Now, one of the things you're going to have to be able to do is to use your calculator to evaluate powers or work with exponents. So 2 to the 1/4 power, you should get 2.639 if you round to 3 decimal places, as they're asking us to here. And you just want to make sure that you want to be familiar with that caret symbol. That's this symbol here. That's what most of you are probably using. Some of you may have a calculator that has something along that line there. But either way, you should be able to use one of those buttons to find the value here. So for the second one, you should get 2.665. And basically you're putting in 2 and then second x squared, and then you put in another 2. And then finally on the last one there, you should get 0.033. Now in that case, the button you're going to want to use, although there are really a couple of options, you may have an E button on your calculator, but for most calculators you're going to hit second and then you're going to hit the LN button. And you'll notice right above the LN button you have an e to the x, and that's for raising a power, or e to some power, and that's what we're doing here. So when you use that button, you should get the answer we have here. Alright, so now let's go ahead and graph an exponential function. So anytime we run into a new function, we can always make a table of values and pick some x values and solve for y. And by doing that, we can get an idea what this function is going to look like. So let's go ahead and choose x to be 0. So f of 0 will be 2 to the 0 power. And of course that's 1. And f of 1 would be 2 to the 1 power, which is 2. And if we plug in 2, of course 2 squared is 4. If we let x be 3, 2 to the 3rd power would be 8. And if we let x be 4, you would get 16. You just keep multiplying by another 2. And so the graph's going to look something like this on the right. You can see this thing is really growing fast. Now let's see what's going on the left. Let's choose x to be -1. So f of -1 is 2 to the -1. Now there's a property of exponents. It's a to the -n equals 1 over a to the n. Notice a negative exponent doesn't result in an answer that's negative. We have a positive answer here. What I always tell students is negative exponents lead to reciprocals. That's what we have here, 1 over the same base to a positive power. So let's go ahead and use this rule here. It's going to be 1 over 2 to the 1st power, which is 1/2. And there's actually a nice pattern here. If you write it out, 2 to the 4th power is 16. Of course, 2 cubed is 8. 2 squared is 4. 2 to the 1st power is 2. And 2 to the 0 power is 1. So there's a pattern here. Look at what we have here on the right side. 16, then 8, then 4, then 2, then 1. What's happening, or how could you generate the next number? So going from 16 to 8, what could we do to 16? Well, the pattern is to divide by 2. Notice 16 divided 2 is 8. 8 divided 2 is 4. 4 divided 2 is 2. 2 divided 2 is 1. And so to find 2 to the negative 1 power, we're just going to do 1 divided 2. Well, that's what the number 1/2 can be thought of as a division problem. For 2 to the negative 2 power, we're going to take a half and divide by 2. And dividing by a number is the same as multiplying by the reciprocal. So we get a half times a half, and if you multiply across, you get 1/4. So this is equal to 1/4. So what I want you to notice here, notice 2 to the 1st power was 2. 2 to the negative 1 power was a half. Again, these are reciprocals. 2 squared is 4, and 2 to the negative 2 is 1/4. So hopefully by now you can see the pattern. We know that if 2 cubed is 8, then 2 to the negative 3 would be 1/8. And we know if 2 to the 4th power is 16, then 2 to the negative 4 power is 1/16. And so let me go ahead and add these 2 points, negative 2/4 and negative 3 1/8. And let's go ahead and put those on the graph. Now if you did negative 4, you'd be at 1/16, and then negative 5, you'd be at 1/32. So you just keep getting closer and closer to 0, but you're never going to get there. It's going to look something like that. What we have here is an asymptote, just like when we were graphing rational functions, and that would be y equals 0 here. And so our domain, notice there is no leftmost point or rightmost point, and we're hitting every point in between. So the domain is all real numbers. Again, we always talk about x values when we're dealing with the domain. So what we're saying is if you look at all the points on this graph, we're hitting every x value. And that's because there is no left or rightmost point. Now for the range, we're going from the lowest to the highest point and looking at y values. Notice the y value never quite reaches 0, but there is no highest y value because the graph goes up forever. There is no highest point. And so 0 to infinity is your range. And of course we said y equals 0 was the horizontal asymptote. Now again, the big feature of this graph is it has what we call exponential growth, which means it's growing super fast. It's like if you put a bunch of rabbits out in some community, next thing you know, you're going to have a ton of rabbits. They grow fast. They grow exponentially. That's the idea. Let's go ahead and move on to example 5. But before we do, I want to point out we really don't need all these points. The main point is the y-intercept, and then it's good to have a point on each side, and so that's what we're going to do. We're just going to find 3 points to graph these, and that's plenty of, that's enough. Alright, so here we're going to let x be negative 1, 0, and 1. Of course, 1/3 to the 0 power is 1. 1/3 to the 1st power, anything to the 1st power is itself, so that'd be a third. And then, well, let's see, let's find f of negative 1. That'd be 1/3 to the negative 1 power. And there's another property of exponents that's useful here. If you have a fraction a over b to the negative n power, that's actually equal to b over a, oops, I forgot my, hold on a second, forgot to put in my n here. So in this case, this is 3 over 1 to the 1st power, and so that's just going to be 3. By the way, I want you to notice that these are reciprocals, and they always will be. And so if you know one, you'll always know the other. You don't have to do the work even. You just find the first one, and then you know the other one will be the reciprocal. Alright, so let's go ahead and plot these points. We know we're going to have an asymptote at y equals 0, or you can see that here. As we draw the graph to the right, again, if you put in like a 2, it'd be 1/3 squared, and you end up with 1/9. If you put in 3, you'd be 1/27. So you get closer and closer, but you never reach. So it's going to look like that. Our domain is all real numbers, and our range is 0 to infinity, and the horizontal asymptote is still y equals 0. This is what we call exponential decay. Notice going from left to right, this thing it decays quickly, and then after a while, then it takes forever for the rest of it to go away, or it just takes forever to get to 0. It doesn't quite get there. Alright, it just approaches 0. Alright, let's move on and let's summarize here. So with exponential functions, it's basically of this form here. And we know our base has to be positive, can't be 1. When we graph these, we're going to choose -1, 0, and 1 for x. Y equals 0 is going to be a horizontal asymptote. If you look at the first one we did, it was y equals 2 to the x. The function was increasing. It has that shape. It's what I call exponential growth, or what we call exponential growth. If you have a situation like the last one we did, where the base was 1/3, the number is positive, but it's between 0 and 1, that's where the graph is going to be decreasing. It goes the opposite direction. It's a decreasing function. And in both cases, the domain's all real numbers, and the range is 0 to infinity. Alright, before we get started on the graphs that we're going to be doing, I just want to remind you about how we do the graphs of transformations. So let's look at an example here, f of x equals x squared, which we know is the graph. If we graph it, we get a parabola. So it says, recall that if you have f of x plus some number separate from the function, it causes the function to go up k units. So for example, in our case, if you had g of x equals x squared plus 2, we know what x squared looks like, and that plus 2 would cause the graph to move up 2 units. So that's what it's saying here. F of x minus k would be the same graph moved down k units. So for example, our graph, if you have x squared g of x equals x squared minus 1, it'll look just like our function f of x equals x squared. Everything would just be down 1. And then we have f of x plus h. Now because the h is inside with the x, it's going to cause a horizontal shift. An example would be g of x equals x plus 3, quantity squared. And we know in a case like this, it's going to go the opposite direction of what we might think. So plus 3 there, I'm thinking it would go right 3, but it actually goes left 3. If you had g of x equals x minus 4 quantity squared, then that would go right 4. Again, it would be the opposite direction of what you might expect. Minus f of x, if you have a minus out in front of the function, it causes a reflection over the x-axis. I always use this symbol here to represent that. So notice minus x squared, it actually would have a graph that looks something like that. And then for f of minus x, notice the minus x is now inside the function. So it would look almost exactly the same here. Notice my base is minus x. The minus is with the x. It's not out in front of the function. And so this causes a reflection over the y-axis. In this case, if we reflected y equals x squared across the y-axis, we'd end up with the same graph. It just happens to be that way with this one. And with these, our symbol goes this way. Alright, let's move on and do some problems. So first of all, we have a base of 3 here, so our parent function is going to be y to the 3, or y equals 3 to the x power. So the base determines who's the parent. So let's go ahead and make a chart for our parent function. And of course 3 to the 0 is 1, 3 to the first power is 3, and we know that's going to be a third. Let me go ahead and plot those points. We know we have an asymptote there. And so now we just need to look at that minus 2 here and decide what's going on with that. Well, that's going to cause a horizontal shift because the minus 2 is with the x. It's going to be the one that works kind of backwards. So you're going right 2. Let's move our points right 2. Notice if you move the asymptote right 2, that doesn't change anything. And so our graph's going to look like that. Our domain is still all real numbers, and our range is still 0 to infinity. So you might want to try the other one and then watch the video. Alright, so here we're using the same parent. This plus 3 is separate from the exponential function 3 to the x, and so this causes us to go up 3. It's a vertical shift. So we're going to move all our points up 3. And let's now keep in mind, if you move the asymptote, or if you move the graph up 3, the asymptote will also go up 3. And so it's going to look like that. And there's our graph. And so our domain is still all real numbers, which it always will be with an exponential function. And notice our lowest y value, we don't quite hit 3. It'll be 3 to infinity. There is no highest point. Alright, let's look at number 8. So we have a new parent function, y equals 2 to the x. Let me make a table for that. We let 2 to the 0 power is 1. 2 to the first power is 2. And of course we know that's going to be a half. So I'm going to go ahead and put those points on the graph. Notice the minus is out in front of the function, so it's going to cause a reflection, and it's going to go through the x-axis, so it'll reflect down. So 0, 1 reflects down to 0, negative 1. Notice here we're up 2, so we're going to have to go down 2. That puts us here, and then here we're up like a half, so we're going to be down a half. That puts us there. And that's all we've got, so that's going to be our graph. Notice our domain is all real numbers. There's no left or rightmost point. Our lowest point, that's where we're going to start, and the y value there, well, it goes down forever, so there is no lowest point. So that would be negative infinity. Oops, I need to fix that because we actually only go up as high as 0. Hold on a second. There we go. Alright, so let's look at example 9 now. In fact, again, I would encourage you to maybe try that one and then listen to what the video has to say. Alright, so same parent. Notice this time we have a reflection across the y-axis because the minus is with the x. It's not out in front of the function. And that minus 3 is going to cause a vertical shift down 3 since the 3 is completely separate from the function and from x. And so let's see, we're going to move all our points. Well, first of all, I need to remind you that we always reflect first. So let's reflect now. 0, 1's not going anywhere because it's on the y-axis. So this point here is going to reflect across the y-axis to there. And this point here will reflect across the y-axis to there. And so the graph's going to look like that. Now I made it dotted because we still have to move every one of our points down 3. So let's go ahead and do that. And again, if you're moving the graph down, you're going to have to move the horizontal asymptote. It needs to go down as well. And so your graph's going to look like that. Alright, so that's a domain of all real numbers. Notice we go as low as -3, don't quite get there, and then it goes up forever. No, there is no highest point, as you can see here. Alright, we've got 2 more to go. Alright, so we're graphing e to the x. It looks kind of complicated. It turns out e is a nice base to work with, and later on we'll talk about logarithms, and base e logs are very easy to work with. And so this number comes up a lot in nature, or when you're doing the kind of arithmetic or math that engineers would do. Anyway, it's a number that's about 2.718. It's kind of like pi. When we work with circles, we use pi. There are a lot of cases where we can use this number e that we call e. So let's go ahead and graph this. Let's make a table, and again, same x values. Of course, e to the 0 is 1, and e to the 1 is itself, so that'd be 2.7 about. And to find e to the -1, you probably want to put that in your calculator, second ln, and then put in -1, and you should get 0.4. Alright, so let's plot these points. Our asymptote's going to be right there, and let's go ahead and draw that. So domain is still all real numbers, and the range is 0 to infinity. And this isn't surprising at all. We've graphed 2 to the x power, we've graphed 3 to the x power, and isn't the base 2.7 in between those two? It looks quite close to what we've already graphed. And so on number 11, we're going to use the same base, so we just graphed the parent function here. And so now we know the +3, actually I'm going to go ahead and put the parent on there. The +3, x plus 3 there causes a horizontal shift left 3, and the +1, which is totally separate from the function, causes a vertical shift up 1. And so let's move each of our 3 points left 3 and up 1. It actually doesn't matter which way you go first, up 1 or left 3. I went left 3 and then up 1. It doesn't matter. But anyway, so if we're moving up 1, now moving left 3 won't change our horizontal asymptote. Moving right or left won't change it, but going up, that's going to move it up 1. And so our graph's going to look like that. Domain's all real numbers, and notice our range is adjusted a little bit. It's 1 to infinity. And that's the end of this video. We'll stop right there.